Okay, surface integrals and flux integrals. What the heck are they and what are they used for? Good news, you already have done a surface integral already, but I never told you that that's what you were doing. Really? Yeah. So let's talk about what you know, and then we'll go with what you don't know. So let's do a quick summary of the different kinds of integrals we've done in this class over the last month or two. Line integrals. You've done some of those in this chapter 17. Those are evaluated along what? What are you evaluating along when you do a line integral? Anybody know?
Curve.
Curve. Very good. Yeah, you're a curve. They call them line integrals. So it's like, well, you evaluate along a line. Well, curves. Okay. Double integrals are typically defined on what?
Region.
Regions, which are areas, right? And then triple integrals are defined on
Volume.
close
The solid.
solids. You might use a triple integral to find the volume of a solid, but you might use it to find mass, or pretty soon you'll see on Wednesday, you might use a triple integral to find divergence, which is cool. Okay, now today we're going to look at an integral over of a function over a surface, but I claim you've already done a surface integral. You've done a very basic surface integral. We have, yeah, when I made you do 17.6, and I actually, it was a portion of 17.6. I didn't have you do all of 17.6 because that's what we're doing right now. The little portion of 17.6 that you've already studied is using a double integral to find surface area. Remember? So here, here's the review. If you've got a function f and all its partials are continuous on some closed region R in the xy plane, the area of that surface S is given by z equals f of xy over r is given by, I should rewrite that. And it's the surface integral. And how do you tell? You've got a big S right there. And the integrand is a 1. But what's d big S? That doesn't mean that you're integrating with respect to S, okay? This big old ds is the surface area element. It stands for surface area element. So what do you replace the big ds by before you even try to integrate? This big old radical that I even went through and derived for you. It's the square root of 1 plus the partial of f with respect to x squared plus the partial of f with respect to y squared dA. And dA is the area element. And if you're in rectangular, that would be dy dx or dx dy. But if you were converting to polar, what would your area element dA be? R dr d theta, right? Okay. Now, so I'm not going to redo surface area double integrals because you're already knowledgeable about that. But we're going to use this surface integral that's got the surface area element in it to help us find the mass of a surface given by z equals g of xy, where the density is given by f of xyz. So keep in mind, this is the density function, and it's a function of 3 variables. And this right here, we're going to change his name. Back when I first covered the surface area stuff, we used f. But f, we're going to use f for the density function. Let's change the capping surface to be a function of g, or function g of xy instead, if you don't mind. And it's going to get a little confusing because you've got the function f and then you've got the function g, and it's like which one is which. And that's a common student error when they do surface area integrals, is they screw up and get confused about which one is which. And you don't want to do that because then you'll blow out a big part of your final exam. So let's do the surface area integral. This is also known as, aka also known as, a scalar surface integral. As opposed to what? As opposed to a vector surface integral, flux surface integral that we're going to do in this section also. So there is a difference. Just like with line integrals, we had a scalar line integral, and then we had the type 2 and 3, which were the vector line integrals, vector fields. Here, you'll notice there's no vector field involved in this particular surface integral. And when we do the other type, there will be a vector field. So there is a difference. So you got some surface S that's given by the equation z equals g of xy, and let r be the projection of this capping surface onto the xy plane. And then you need g and his partials to all be continuous on the region. And then f x, y, z, this is the density function for that surface. Hopefully that's continuous also. Then the surface integral of f over s is given by, now here's how they're going to give it to you, but you're not going to actually integrate this double integral. You'll see two double integral symbols and an s down below. And then you'll see the density function in the integrand instead of a 1. And then you'll see d big S, which means don't integrate with respect to big S. It means that's the surface area element. But you can't actually integrate that. So what you do is you turn it into a regular double integral that you can integrate. And you turn it, it's going to be integrated over a region R, which is the projection of the capping surface onto the xy plane. The density function will stay the same, but then you've got this big old surface area element. So you're going to replace the d big S with square root, big old square root, 1 plus the partial of little g with respect to x squared plus the partial of little g with respect to y squared. And then you have the area element, dx dy or dy dx. Okay? Now, we'll talk about an issue here in a moment. But first, let's talk about, no, I think I better talk about it now. Okay, this is a double integral. Yeah, not a triple. But when you do double integrals, you're only allowed to have two variables. And usually we use x and y. If you convert to polar, then your double integral uses what variables? Not x and y, but what? I'll open it up.
R and theta.
R and theta, very good. R and theta. So what the heck here? Do you see something weird about what I just wrote down here with this, this double integral over the region R? Do you notice that we have more than two variables that are showing up there? I have x's, y's, and a z. What the heck? You're not allowed to have that. That's like bad. So what you're going to do is you're going to replace any z's that you see, and there may not be any z's. Like if it's a real easy problem that Briggs has, they may give you a nice density function that only has x's and y's. Then you don't have to worry about this replace thing. But you know me, I don't like picking those. I'm going to give you the homeworks and the exam problems where there will be a z in the density function, and you better replace that z with g of xy from the capping surface, okay? And if you don't, you're going to get screwed. So that now then everything will be just in x's and y's. Okay, now what are some common student errors that I've seen over the years when a student does one of these surface integrals? Well, one of them is they forget to replace the z from the density function with the g of xy, and that's a big mistake. So that's one error. Another yucky mistake that I see is they accidentally use the density functions partials when they're doing this big old radical with the surface capping surface partials. So I'll write that down. They accidentally use f, x, y, z's partials and put put those in place of the gx and the gy. So these are supposed to be the capping surface partials. That's who you're supposed to put inside the radical. Okay, so those are two common student errors. Now I'm pointing them out in advance in the hopes that you won't do either of these two silly mistakes, although you never know. When I teach this, sometimes students fall into the death trap anyway. And it's like, hey, did I not point out these two possible pitfalls to you so you wouldn't do them? It's like, oh, I forgot. Oh, dear. I tried. Okay, now I'm going to do some examples. So these are classic examples of explicit surface area, surface integrals, okay? And the only real application is finding mass of a surface. Just so you know, it's not like, you know, something else. Okay, so we're going to evaluate this surface integral. How do I know it's a surface integral? Well, I got a big S down there. And it says D big S. Okay, now the surface that we're doing the surface integral over is going to be the first octant portion of this plane. And you guys know how to sketch planes because you've been in the class now for, what, 3, almost 4 months. And so if I find the x-intercepts, what's the x-intercept here?
3.
1, 2, 3. Put a dot. What's the y-intercept?
6.
2, 3, 4, 5, 6. And what's the z-intercept?
3 as well.
And so the first octant portion of the plane is this sort of slanted portion, triangular portion in the first octant. Fine, that's our surface. Okay, now the problem is, before I set this up, is that we're going to need to solve for z, because you need that. You need z, which is your little g of xy in the theorem on the previous page. So just look here. We need that z equals little g of xy first. So that's easy to do. So if you subtract the 2x and the y from both sides of the equation and then divide both sides by 2, there's your z, which is your little g. And so for the theorem, you need to get the partials, and this is pretty easy. The partial of g of xy is, you got to have that half. And then taking the partial, you get -2. Oh, it's a constant. Oh, that's nice. And then the other partial, little g of y, you got the half, and then -1, and that's going to be, okay, -1/2. Fine. So now we have our little gx and our little gy, and that's what we're going to put in this big old theorem here. That's going to end up going under the radical and getting squared and then added to a 1. Okay. Let's do the radical right now. Let's just do some algebra work because you're going to have to do this mess here anyway. So why don't we go and clean this up? It's not too hard. You just got your 1 plus the sum of your partials getting squared. Okay, fine. And when you square a negative, you get a positive. So I get 1 plus 1 plus a fourth. And that ends up adding up to what, 9/4. But then this is square root of 9 over square root of 4. Oh, it's just a constant that we get for the radical. Does that always happen? Oh, no, it does not. But if it does, it's like, yay, that's good news, because that might mean it's pretty easy to integrate. Because the pitfall could be also is that when you set up this surface integral, it could be something so yucky it's not really integrable unless you know, try to do something nuts. I don't know. Okay, so now what do we have here? So this surface integral that we're trying to do becomes a double integral over the region, and then we're going to have y squared plus 2y. Why don't we replace this z right now? Because I should. I don't want to have any z's in this double integral. So the z that I have is 6 minus 2x minus y all over 2. And the good news is that these 2's cancel, so that looks a little bit nicer. And then you're going to have your ds, but we just got your ds, that's 3/2, and then of course dA. So this problem isn't too hard, and I'll just kind of wrap it up here. What am I going to do? I'm going to probably want to distribute this y over the parentheses, and then we'll clean that up. But also, what about the region in the xy plane? Well, if you look at the projection of this capping surface onto the xy plane, it'll be this triangular portion right here. So if I look at that, That's my region R. Okay. So what is the, what are going to be the limits? I'm going to choose dy dx to be my dA. That's my favorite order of integration. You may want to do dx dy, but just be mindful of which one you choose. So let me do a couple things at once. Once I distribute the y, oh dear, I'm going to have, what do we have? A y squared plus 6y minus 2xy minus y squared. And then I'll choose dy dx to be my order. And then x is the outer integral. It looks like x is going from 0 to 3. What's y doing on this triangular region? You put your little man in here.
0 to that line.
0 to the line. Yeah. And so what is that line? Well, if you let z equal 0 in your plane equation, that'll give you the trace as that surface cuts through the xy plane. So it's 2x plus y equals 6 after setting z equal to 0. And then if I solve for y, I get the function of x, 6 minus 2x. And that's going to be my upper limit for this double integral. Now, good news, these y squareds cancel. Sweet. And so then, and then I also have this 3/2 I better worry about. Let me just put him in the front because he's kind of bothering me. And then I only have to integrate 6y minus 2xy with respect to y. And let's see, what do I have here? 3/2 integral. Let's see, I think I'm going to get 3y squared minus xy squared, going from 0 to 6 minus 2x, so that you can see this is going to get pretty messy when I substitute my limits. The 0 is just going to have both those terms go to 0, but this is going to be pretty bad. So let me just see something here. I want to show you a little trick for yourself if you are interested in seeing this. Would you, let's just do a little scratch here, down here. Would you agree that 6 minus 2x is the same as 2 times 3 minus x? Would you agree with that?
I agree.
Yeah.
Okay. So unless you like pain, and by the way, you can do all the pain. If you FOIL this out and then FOIL this out and then distribute and then get one big old polynomial, add like terms, la, 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 you'll get it. But if you want a quick little trick, and this doesn't always work, depends on the problem. But what I'm noticing here is that this 6 minus 2x squared is really 2 times 3 minus x getting squared. And then I have minus x. And then this other 6 minus 2x getting squared is 2, 3 minus x getting squared. Okay, so what? Well, you see, this is looking like 3 times 2 squared is 4, 3 minus x squared. And then this 2 getting squared is also going to be a 4. And then you 3 minus x squared. And what I'm going to do, so you can kind of see what I'm up to, is first factor out of 4, like this. And I could do something else quick, but I just want you to kind of see what's going on. Like this. Okay, so the 4s are kind of like, okay, those 4s are out. Now what? If you look at what's inside my brackets, do you see that 3 minus x squared is a common factor to both of those terms?
Yeah.
So what if I pull it out? Then what's the other factor?
Minus x.
Yeah. And then what? Well, hell, let's just combine those 3 minus x's into a single power of 3 minus x like this. And then I claim, and we still have a 3/2 sitting out in front, I claim you can use u sub and the power rule to integrate this without having to, FOIL and all that other business. So, if you let u be 3 minus x, then du is -1. Yeah?
Yeah.
Pull the 4 out in front. And so this is really looking like u cubed du. And you can take it from there. I think you know how to finish out. But anyway, I'll just say et cetera, do the rest of the calculus. And then your final answer for this problem turns out to be 243/2. Okay, final answer for the problem. So that's just a nice little trick that if you notice it, it's helpful. Algebra. But sometimes being a good calculus student is also being someone has good algebra skills. Okay. Any questions on that problem?
Just scroll down so I can see that scratch work again.
Yeah, sure.
Thank you.
It's just some fun algebra. Well, I should say we put the fun in fundamental. Uh,
Oh my God.
yeah. I saw some comedy the other day and they said, we put the fun in funeral. Put on pop. Okay, that's not good.
Okay, I'm good. Thank you.
Yeah, okay. All right, so I just blew over example 2. And so we'll start example 2, I guess, right here. There's my meme. I used to be good at math, but then I took vector calculus. Ha ha ha. Some of you may feel that way. I don't know. What's the deal? We're in a hard chapter right now. I was talking with a student last week, and they were telling me, you know what? I hope I never see this crap again. That's hilarious. I love it personally. But I think that part of the complaint for the student was like, there's just so much crazy notation. And I went, yeah, I know. You got the D little s, which is the arc length element. And now we got the D big S, which is the surface area element. And then you have dA, and then you have dV. Then you have dV if it's spherical, which is rho squared sine phi d rho d phi d theta. I mean, this is why I encourage you to make a cheat sheet for your final, because then you'll have a better chance of success. Okay. So we're going to evaluate this surface integral for example 2, x squared z ds. And the s, the capping surface, is the portion of this cone, z squared equals x squared plus y squared, which lies between the planes z equals 1 and z equals 4. I'm going to actually draw that first. So the cone, if you actually go to GeoGebra or whatever, it's a double napped cone. It's got like a cone facing up and a cone facing down. That's z squared equals x squared plus y squared for you. But then they want it to be bounded by z equals 1 and z equals 4. Well, z equals 1 is a horizontal plane that's just parallel to the xy plane. It's flat. And then z equals 4 is another parallel plane, parallel to the xy plane, that is. And so what does our solid look like? I should say surface, but it could be a solid if we took all the surfaces. So if I try to draw after taking all of these in account, what we're really seeing is it kind of looks like a funnel, actually. It looks like the portion of a cone that lies between the z equals 1 and the z equals 4. So that's our surface right there. So we're just talking about the surface. It doesn't have a top or a bottom. It looks like I closed off the surface, but really I did not. It's just the lateral side of this, this funnel, if you will. Okay, that's the surface, big S. Fine. Now we have to rewrite big S. Well, what do you mean? Well, this z equals x squared plus y squared. Come on, Surface Pro, you can do this. I'm in erase mode now. We're going to have to solve this for z. And when you do, you get 2 answers, of course, because of this taking the square root of both sides of the equation. But because we're taking the upper portion of that double napped cone, we'll only worry about the positive. And then further, this is the little g of xy in the theorem. So don't get confused about blowing this and thinking that this is the density function, because they gave us the density function. X squared z is the f xyz in the theorem. So you don't want to get just confused between f and g. Okay? So now what? I need to get little gx and little gy. I need to get those partials. So I'm going to have 1/2 times the quantity x squared plus y squared to the negative 1/2. And then I'm using the chain rule and I'm taking the partial with respect to x. So times what else?
2x.
And then you can rewrite this and clean it up and simplify it. And I would. In fact, I'll put the radical back in like so. And you can do a similar thing for finding the partial with respect to y. And you're going to use the chain rule again. So you're going to have a 2y factor. The 2's cancel. Lovely. And then you'll have, after reducing it and rewriting it, I get this. Okay, fine. Okay, so now what? Well, I need another page. Okay, so let's do, we're continuing here. What is this radical going to look like? Let's clean this up because that's going to be kind of gross. So using what I have there, I got 1 plus x over square root of x squared plus y squared squared plus the y over square root of x squared plus y squared squared. And this looks pretty horrible. It's like, oh no, you're kidding me. This is going to be a nightmare. Are we going to ever be able to actually integrate this double integral once we get everything going? Because I don't want to use
Gonna
trig
equal
sub.
2.
Mm-hmm. Yeah, you'll combine these because they have the same denominator, and then you'll notice, hey, that reduces to a 1, and so really you're just going the square root of 1 plus 1, which is square root of 2. Fantastic. Does that always happen? No, it does not. It does not. So what are we saying? I'm saying that this surface integral is going to become a double integral. This ds is really going to become square root of 2, that was this thing here, dA, and then you're going to have the density function x squared z. But you know, I don't like z's. That's not cool. I don't want to see a z in a double integral. Maybe a triple integral, but not a double. So what do I replace the z with?
Square root x squared plus y squared.
Yeah, you need to replace him. It's like, oh man, this is looking really gross. Then what also do we need to do? What's the region R? Because this, do you see this surface never touches the XY plane? It just doesn't. It's hovering way up there, you know, it's hovering in space. So what's the region in the XY plane? Well, it's the shadow that this capping surface makes on the XY plane. It doesn't touch the XY plane. And so what's the shadow look like? Well, I claim
Circle.
it's going to look like concentric circles. Concentric circles.
Oh.
Really? Ooh, be careful. So one of the concentric circles is when you plug z equals 1 into the z squared equals x squared plus y squared. That's one of the circles. Cool beans. And then what? Well, you plug z equals 4 because that was the other horizontal plane that was capping above. And then you plug that into your x squared plus y squared. And then you get the other circle. Aha. So that's the shadow or the projection of this funnel on the XY plane. I hope you can appreciate that those are just going to be circles of radius 1 and radius 4 respectively. So here's your region, big R. So when you turn this surface integral, which has a big S down here, into a double integral over the region, this is the region we're talking about. So this is what we're doing right now. So any ideas on how we're going to integrate this?
It's polar.
You're going to convert to polar. Very good. Otherwise, forget it. You're definitely going to want to convert to polar. So what are the limits for R and the limits for theta on my region R? Let's distinguish those right now.
For theta, it would be 0 to 2 pi, and for r, it would be 1 to 2.
Careful.
1 to 4.
1 to 4, because we plugged in 4, and that was 4 squared. 1 to 4. Okay. So you're going to go, okay, 1 to 4, 0 to 2 pi. I'm going to pull this square root of 2 out in front. What do we replace dA with? Think like a pirate.
Arr.
R. drd theta. Okay. How about this integrand? How do we convert that puppy to polar?
X equals R cosine theta.
Good. And square root of x squared plus y squared?
It's R squared.
Close?
Oh, right.
Like that?
For what?
Which is just R. So now what I would do is I'd combine all of your R's into a single power of R. And you got a lot of R's here. You've got this R, you got this R, you got this R. Hold on a second. Did I forget an R? Oh, this is x squared. I almost forgot. This has to be R cos squared. Whoopsie daisy. You guys didn't even notice. I screwed up. So make sure you take these x's and put a little exponent on there because the original problem had the density function with x squared. My bad. So this is really R squared cos squared. And so when I combine all my R factors into one big old R, I'm going to have, I'll still have a co-squared, I'll have R to the fourth. Okay, now I can integrate with respect to R. You got to be careful here. You got to pick up all those R factors. Okay, so the antiderivative of R to the fourth is pretty easy. It's R to the fifth over 5, and we're going to evaluate between 1 and 4. So this is not going to be pretty because you'll have 4 to the fifth over 5 minus 1 to the fifth over 5. And I claim that's 1,023 fifths. So, wow, that's weird. And it's just a multiple, so I'm just going to put it out in front of my integral, and then I have to worry about integrating co-squared. And you guys all know what you think co-squared is going to be on the midterm? Most likely. At least you got to have at least one of those because I'm really into it. So what do you do with co-squared when you're integrating?
It's power reduction.
Power reduction. Yeah, you should know this by now. This is like, you're on automatic now. I'd pull this half out in front, and then after doing that, you're going to have the integral of 1 plus cos 2 theta is theta plus a half sine 2 theta. Evaluate that between 0 and 2 pi. The sine term doesn't contribute anything because it's 0 both times, although the theta contributes 2 pi. And so then after reducing this to lowest terms, I get a really weird number, 1,023, square root of 2 pi over 5 after reducing, and that's approximately 909.0. Fine. Questions?
Nope.
So those are the only two problems I'm going to do for you with regards to scalar surface integrals. Now we're going to move on to the flux version, the flux integrals, which is basically a surface integral involving vector fields. I do want to say that I am not teaching you parameterization of surfaces, although other professors who teach Calc 3, I think right now they are. So you don't have to parameterize a surface in my class. You're welcome.
Thank you.
Yeah, that'd be a lot more material for you. Yeah, figure it's bad enough. We got enough on our plate. Okay, so let's do a quick summary of what we just did, in case you were falling asleep and didn't have enough coffee. The scalar surface integrals, you've got some function f defined on the surface, and that's supposed to be like a density function. If it's just a 1, then, and you basically have a 1 here for your surface integral, that actually gives you the area of the surface. And you saw this already in the last midterm, because I asked you to use a double integral to find surface area. So, but if you put something other than a 1 in that surface integral, then it's not going to represent surface area anymore. Typically, the application would be mass. So if you do a rho, and this rho is a Greek letter. It's the same rho that you saw in spherical, but it doesn't mean anything to do with spherical. Well, how come they keep using a rho? A lot of textbooks do. You use a lot of Greek letters. This is not the letter P. Please do not call it a P. It's a rho. Well, how do you tell the difference? Well, a P looks like this and a rho looks like that. Okay, know the difference. So rho and I've been doing the last couple problems I've done, I've used an F instead of a rho. Whatever, it's just notation. That would be some density function. And so then if you see a scalar surface integral like this, this would represent the mass of your lamina, your surface that you're working on. Okay, fine. Now let's move on to the second type, the second half of this lecture, which is probably the more important part of this lecture, because most physics folks rarely do scalar surface integrals. They're more concerned with vector fields, so they're more into flux. And flux integrals are just basically a surface integral that you use to find flux, which we'll talk about in a second. Hold on a minute. We'll get there. First, let's talk about orientation of a surface. Okay, when you have a surface, there's such a thing as orientation. Really? Well, you guys have heard the word orientation before when you're talking about a curve. So like if you have a curve like, let's say a parabola, it could be oriented, in the sort of forwards direction. On the other hand, it could be have an orientation going backwards. So that's curves. But what about surfaces? You can actually orient a surface. That seems weird. Yeah, you can. So here's how you do it. You get a surface and you orient it with unit normal vectors, which you already know what those are because you used normal vectors to find tangent plane equations. So we already studied this. It's old news. Really? I forgot. I know you did. Don't worry. I'm going to do a review real quick here. So you're going to induce an orientation on a surface with these unit normal vectors. Okay, here's some definitions and then we'll get to it. A surface is called orientable. And by the way, this has nothing to do with the orient, okay? It's just a word. If a unit normal vector, big N, and you've seen big N, you already know what this is, can be defined at every non-boundary point of S in such a way that the normal vector is very continuously over S. That says a lot, but what does it mean? Well, I'll do a picture in a moment. Hang on. If this is possible, then S is called an oriented surface. Okay, now this N, by the way, is not the same N that you used with vector valued functions. So I just want to say this is not the N equals big T prime of T over the magnitude of big T prime of T. Well, which N is it? It's going to be the unitized version of the gradient. So big N is going to be del big F unitized. Okay, and we found del big F when we found a normal vector to a surface. When the heck did we do that? We've done so much this semester, I forget already. I know, right? This was 2 chapters ago. It was chapter 15, and you used del big F as the normal vector to your tangent plane. And we had to get tangent planes. And if you forgot all that already, well, this is a good review for the final because you're going to have to do one of those on the final. Hey, okay. Now, here's the weird part. I always thought that this is like fascinating. I just can't get my mind around it still. An orientable surface has 2 distinct sides. And you may think, well, all surfaces have 2 distinct sides. Like this piece of paper I'm holding up in front of you now. I don't know if you can see my camera. It's got 2 sides to it. It's got this top and then it's got underneath. So it definitely has 2 sides, this piece of paper. You know, and a sphere has 2 sides. Like here's a sphere, okay? You got the outside, you know, with little unit normal vectors that you could create punching outward. These are little unit normal vectors that are punching out of the sphere. And then if you had a little gnome or leprechaun, he'd sit inside of the sphere. You've got the other side of the surface of the sphere, the inside. So you could create little normal vectors that are pointing into the center of the sphere. So this sphere definitely has 2 distinct sides or surfaces, an outside surface and an inside surface. But not all surfaces have 2 distinct sides. So really, no, they don't. Have you ever heard of a Möbius strip?
Yeah, it's that.
Möbius strip, yeah.
It's the figure 8 strip.
It's a figure 8 strip that does not have 2 sides. You can start like a little bug walking on one side, and if we were face to face, I'd rip off a piece of paper and I'd show you this. But in zooming, it loses all translation. But it's a piece of paper that you sort of make a twist in it and then hook the 2 ends together, and it doesn't have 2 sides. It's like not orientable. But in this class, good news, we're not going to worry about Möbius strips. Okay, screw that. We're only going to worry about surfaces that actually have 2 distinct sides. Yay for us. Okay, we will, in fact, use the gradient vector, just like I did here. The gradient, we'll use a unitized version of the gradient vector to find the unit normal vector. Okay, so now let's get to it. We're doing some prep work for Flux. So keep the idea of like we're trying to learn what a flux integral is, and that's what we're going to finish up with hopefully today. So I can do the divergence theorem on Wednesday. Yay. So if little z is some orientable surface, then rewrite it. Get all the crap on one side and 0 on the other. A Klein bottle. Yeah, you know, Chris, I have no idea, but you could be right. I'll have to look into that. Interesting. Okay. Do you guys remember a couple chapters ago when I would give you like z equals little f of xy, and I told you before you go get the gradient, would you please be so kind as to subtract the z from both sides and get 0 on the other? And then you call this big F X, Y, Z. Do you remember this whole process? And then you would get big del F of X, Y, Z so that you could get a normal vector to the surface. Does anybody remember this?
Yep.
Okay, so I hope that this was chapter 15 material. Okay, I'm going to change it up just a little bit, but not much. In this chapter, it's always like, well, how come you do it the wrong way? Instead of subtracting z from both sides, and by the way, I didn't even care if you wanted to move all this crap to the other side, just so long as you got everything on one side and 0 on the other, I didn't care. Okay, now I'm going to care a little bit. It turns out that if you want an outward vector that's punching up, you don't want to subtract the z because then this fz would be -1, which means it would be a normal vector punching downward or pointing down. And that's fine too. But most of the time when we do these flux integrals, we'll want upward and outward normal vectors. So they want you to keep z on the same side so that when you take the partial with respect to z, he's a positive 1, and then get all the other x's and y's move them over, and then you get 0 on the other. And this is just the general representation of a surface. You're actually using sort of the level surface representation where the c is 0. Fine. And you already did this in 2 chapters ago. Now what? And by the way, we're changing his name now. So back in chapter 15, I would call it big F of XYZ. And now we're changing the name to big G. I know it gets really confusing. Oh, I'm really confused now. There's too many letters. I can't think. And I'm sorry that there's so many letters and the notation gets pretty busy. But that's vector calculus for you, people. You got a lot of notation and it gets pretty busy. So try and keep up. Yeah. Okay. So I have no idea who Tony Stark is, Aloe, but thanks for sharing. Okay. So if you are given an orientable surface, little z, move all the stuff over to one side, 0 on the other, so that the z coefficient stays positive, and then rename the function of x, y, and z big G, and then get the gradient for big G and unitize it. So that's going to be your n. So your unit normal vector is going to be the gradient of big G, and you want to unitize it. So you guys all know how to unitize. You divide by the magnitude. And so if you look at this function here, when you get the gradient, you're going to go, okay, what's big GX? Big GX. Don't write that down because we're going to just sort of do it on the fly. Big GX is going to be, well, the derivative of z with respect to x is 0. Then you'll have a negative, and then whatever the partial is of little g with respect to x, that'll be your big GX. And then the big GY is going to be negative, whatever the partial of little g was. And then the partial with respect to z is, since there's just only one z there, it'll just be a 1. And then you'll unitize it like this. Oh, poor Zeke. Okay, and this is a unit normal vector oriented up or out. Now, there are times when you might want to orient your unit normal vector down instead. Sometimes you need to do that. Not so much in this section, but on Wednesday, we're going to probably have to do that. So if you take the opposite of this vector, you'll just get the one pointing down. So what does that mean? That means you're just going to take the opposite in sign. So this will be a positive GX, positive GY, and then a -1. And then you'll still have the big old magnitude. That's supposed to be -7. Oh, man, I cannot write. Woo! Okay, and then you still have the big old square root because you're taking the magnitude because you want to unitize it. And you're like, why do we have to unitize this vector? We didn't have to unitize it back 2 chapters ago when we were using it to get the tangent plane. Yeah, I know that, but now you need to. We're getting there, okay? Just be patient. Okay. You can hear Zeke toinking. Yeah, he's crying right now. It's bad. I hear him all the time. Okay. Oh, do I have a meme already? Oh man. Oh, here's a Mebius strip. Oh, I have a picture of a Mebius strip. Here you go. Somebody took his cheat sheet. Looks like a cheat sheet for this class, doesn't it? That's great. And basically he took the ends and connected them together, and that is a Mebius strip, folks. There's one right there. Does not have two distinct sides.
Is there any practical purpose to that?
Teacher said we were allowed to bring a single side paper for notes.
Oh, there it is.
I think that's pretty darn funny. If you get there really is only one side. And if you're not laughing right now, you are taking yourself way too seriously, okay?
I would have loved to see that reaction from the math teacher.
I love this. Yeah, haven't you had a teacher who said that you're allowed like a single side paper for like your cheat sheet of notes? And so this kid really figured it out. There's my single side. I teach. Boy, that would just, I would love to see the teacher's face when the kid said that. Oh my goodness. Hilarious.
One-sided sheet paper. No Mobius strips included. Zero exceptions.
That would have to, there'd have to be a little caveat there. No, none of those Mebius strips. Mobius. Some people say Mobius. I say Mebius. It's kind of like you say potato, I say potato. Let's call the whole thing off. That's a song. Okay, let's move on. Fact. One of the principal applications of a surface integral is relating to the flow of a fluid through a surface. Really? Yeah. And those kinds of integrals are called flux integrals. And our physics brethren care about these very much. That's a lot of what they do is flux. Now, we've already done a little bit of flux in this class. Okay. Really? I don't remember. Look, there was some flux on your quiz you just took for me. What do you mean? Look, when I asked you to find the flux of a vector field through a curve, we did one of those. And so just so you know, flux, and this is a 2D version of flux. If you're asked to find mdy minus ndx, remember? The version of Green's that you use for this was you basically get the divergence, and you take the double integral of the divergence, and that gives you flux. You know, the amount of fluid flowing through the boundary of your region. Remember we did this? Flux?
Yes.
That's another line integral application. So Allo, when we were talking Friday and you asked me what is a line integral application, most of the time it's for work done, you know, which is the circulation version. But there is another thing you can use line integrals for. That's to find flux.
Okay, thank you.
So now you got two.
Yep.
Cool. Okay, so we're going to do flux though in 3D. What we did with Green's here, this is the alternate version of Green's. That's flux only in 2 dimensions. So we're going to jack it up some. Oh, okay, fine. So we're going to look at flux integrals. So first, let's do sort of the penumbra of a derivation. Check out this diagram here. If you can think of a vector field, in this case, let's say the vector field is just like a velocity field for some water, you know, like whooshing. So these vectors here are water that's, you know, whooshing. And here's your surface. And you want to figure out how much fluid is flowing across that surface per unit time. So the way you can do it, if you're trying to just, you know, get the derivation, just look at a very small patch of surface here called delta S, little patch where the force is almost constant as it's whooshing by. Then the amount of fluid crossing the region per unit time, and it would kind of look like this sort of parallelepiped there. It's sort of a sheared box. You set your stopwatch, boom, after 1 second, and you could capture that fluid, and it would look like, you know, the amount of volume of that box. That is your flux, basically, the total volume of the column. Okay. Well, how do you get the volume of that column? Well, you already know that the volume of a column like that is area of the base times the height. And the area of the base is just that little small patch that's on the surface, that little delta S, that surface area element, little mini surface area is the area of the base of that column. And then the height is, if you take this corner and drop down a perpendicular here, this is the height. And so the height turns out to be the force vector project it onto the unit normal vector for the surface. And we just talked about what big N is over here. So don't go, what's big N again? It's up here. Okay. It's this guy right here. You're going to take your force field and project it onto this big N, which is a unit normal vector. So it makes it real easy when you project, because then usually you're just interested in the magnitude of it. Okay, so you've got your height, which is going to be F projected onto N. And so your total volume of the fluid crossing over the entire surface is called the flux of F across the surface S. Great. And how do you get it? You do an integral, because you'd sum up all the little patches, get your Riemann sum, and boom, take a limit. So if you've got a vector field with components M, N, and P, and Briggs is probably going to call it F, G, and H, or whatever. Briggs is annoying. Where M, N, and P have continuous first partials on your surface S, and we want it oriented by a unit normal vector N. So you're orienting your surface because it does have two sides. It's not one of those Möbius strips or anything like that. And I have no idea how to get rid of that. Okay. The flux integral of F across S is given by double integral, and you're going to put a big S here because it is a surface integral, and you're going to take a dot product of F and N and then D big S. And D big S doesn't say, oh, integrate with respect to S. This is the surface area element, that big nasty radical. Now, good news. When you're doing one of these flux integrals, you actually don't even have to calculate that big radical. Well, I thought we had to because, the first half of this lecture, you made us do that big radical. I know, but you only have to do that for scalar surface integrals. It's going to turn out for flux surface integrals, you don't have to. Watch, it's going to go away. What do you mean it's going to go away? Well, just like when we ended up with an F dotted with dr line integral, where the little arc length element got canceled out, the similar thing happens here with these vector flux integrals. So here's the derivation. So imagine your surface, there it is. And then of course you do the rewrite of the surface, because I told you to. You get your function of 3 variables. And then your n ds, the big N ds, looks like this. Here's your big N. Here's your ds. That's the surface area element. But now this magnitude, which I showed you on the previous page, is this big old radical. And the surface area element is the same radical. Oh, interesting. So then what happens? These cancel. Ha, 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 ha. Cool beans. Then what? You're only left with the numerator of the gradient of big G. So you don't even have to worry about unitizing it because that cancels anyway. So here's the theorem that basically tells you how you're going to evaluate that flux integral. See, this definition, even though it's the definition, it doesn't tell you how to integrate it. It's just like, well, here it is. That's the definition. It's like, thanks. There's no info there. That's helpful. Down here in the theorem is the helpful hints. If you're doing one of these surface integrals, you don't have to get the big radical because it ends up canceling. To convert it into a regular double integral that you can actually work with, you're going to, again, project the surface onto the xy plane. So you've got a region, and you are going to take the dot product of your force field, whatever that is, with negative gx, negative gy, and then 1. And that's if your big N is oriented upward. You might be asked on some occasions, just to be ready, to do the integral if your unit normal vector is directed inward or downward. So that just means that you're still going to take a dot product, and I'm just going to change the sign of all of the components of this gradient. That's all. So this is if it's oriented downward. And you're going to rarely do that in this section's homework. In fact, I don't think there is any of the homeworks that I put in there that I can remember that are going to use oriented downward. Pretty much stick to oriented upward. This is the tradition. Okay, so that's your theorem. And that's basically what I'm going to use for the next problem. Okay, so flux integral. And yes, you have to take a dot product here. That is a dot product, not a regular multiply. So you're taking the dot product of two vectors. Okay, great. So I just have one problem here in my examples for you. And of course, there's more that you can go do. I don't have any more that you can go do, but that you certainly could. And this one's a nice one. You'll see. They're all pretty much similar. You get your force field. You get your gradient for your surface. Take the dot product and figure out your region and integrate. That's your flux integral. And you're getting an answer. Now, your answer could be positive, negative, or zero. If it's positive, more fluid is flowing in the same direction as your unit normal vector than is flowing back the other direction. If you get a negative number, that means more fluid is flowing in the opposite direction of your unit normal vector. If you get zero, that just means the amount of fluid that's flowing in the same direction as your big N is getting canceled by the same amount of fluid flowing in the opposite direction. That's all. That's your flux. Okay, so let's just do one example. Let's have a paraboloid. And if I graph this paraboloid, it looks like a downward facing paraboloid like this. And it looks like it actually intersects this surface that we're working with, which is the lateral part of this paraboloid. It looks like it is intersecting the base of it anyway, is intersecting the XY plane. But we're not thinking of this as a solid at all. We're only looking at the lateral surface, not the base. Okay, we're not looking at closed surfaces. That's going to be the next section. So you're just looking at the lateral surface. And if you submerge this paraboloid into, say, some jacuzzi where the velocity of the water would represent your vector field, be some velocity field, how much water is going in this direction? This would be how we're going to orient our little unit normal vectors outward. Okay? And if we get a positive number, that means more fluid is flowing in the outward direction than going back in. Okay? So there's your force field. There's your M, N, and P. And they're asking us to find the flux. Fine. So what I would do first is I would get that you want to get this. This is the vector that you want to get, like this. And notice there are negatives here where the Z is positive. That's how we're guaranteed it'll be going upward and outward. So you want to take the opposite of little gx. So the opposite of negative 2x, that's going to end up being a positive 2x. And then negative, the partial of little g with respect to y. So negative 2y, and then a 1. And so then negative negatives are positive. So you get that. So your flux, and if I write it as a regular surface integral, it looks like this. And I do want you to get used to the notation, but you never actually do anything with that surface integral. You immediately convert it to a double integral over the region, and then you're going to take the dot product of 3x, 3y, and z with the 2x, 2y, and the 1. Okay, so I'm going to do the dot product first, then I'm going to ask you to notice something. So you all know how to do dot product because we did that in like the first week and a half of this lecture. Fine. So you're going to get 3x times 2x plus 3y times 2y plus z times 1, like this. And then dA. That's your area element, and you'll decide in a moment if you're going to stick to rectangular or should you go to polar. Now, when you're doing a double integral, are you allowed to have more than 2 variables? Yes or no?
No.
No. Well, do you see that we do in this one?
Gotta replace it.
You gotta convert your
there's a z in this big mess, and that's not cool. Like, you're not supposed to have 3 variables. You're allowed to have 3 variables in a triple integral. That's totally legit. But double integral, hell no. So what are you going to replace this with?
9 minus x squared minus y squared.
Yeah, this surface thing, 9 minus x squared minus y squared. That would be a good bet. Okay, so you want to do that as soon as you can. Now, and then when you do that, you know, if I were you, I do some cleanup. This right here is 6x squared. This right here looks like 6y squared. And then add all the like terms together. So it's a little cleaner, you know, not much. But I get, what do I get here? I get 5x squared. I'm going to factor out a 5 because it's going to turn out both x squared and y squared terms have a 5 in common. And then I have the plus 9. Okay, now what? What's my region of integration? What's my R? See this R right here.
Is it a circle?
Yeah, it's going to be the projection of this paraboloid onto the xy plane. So if you set z equal to 0 in this paraboloid equation and then rearrange everything, you'll get x squared plus y squared is equal to 9. So it looks like it's a circle centered at the origin of radius 3. And so what are the limits on my r and theta for a circle of radius 3? Quick.
0 to 3.
And theta?
0 to 2 pi.
Yeah.
Mhm.
Cool. So I'm going to immediately convert to polar because I should. The region is circular, so that's a good bet. So then what about this integrand? How do you convert this to polar?
X squared plus y squared equals r squared.
Yeah, 5r squared plus 9. Okay, that looks cool. And then what about my area element?
R dr d theta.
Yeah, r dr d theta, you bet. And so then, of course, you're going to want to distribute your r before you integrate so that you have your r taken care of before you integrate with respect to r. And this is a pretty easy double integral because, you know, polynomial. So I'll just let you finish it up. Yeah, I'm sure you can. So go ahead and do that. And then you should get 567 pi halves, which is a positive number. So what does that tell us about the flux?
There's more liquid flowing outwardly along our shape.
If I plunge that surface into the jacuzzi, more of the jacuzzi water would be going out of the surface boundary than going back in. That's all that means. Positive number. Okay. Any questions on this surface integral? Because I'm only doing one example.
When you were discussing like keeping the z on one side, and for the normal vector, I believe, what was that for?
Oh, that was to make sure that the when you got the gradient, that you get a positive 1 here.
Was that a part of the proof for that theorem?
No,
Deriving?
it had nothing to do with that.
Oh, okay.
No, I would direct your attention right here, George. Back up a little bit.
Yeah.
Back up a little bit where it says to evaluate a flux integral. See, here's your surface right here, little g. And you need to get a normal vector, whether it's punching out or punching in. And you did this 2 chapters ago, although I didn't care which side of the equation you got everything and 0 on the other. But now I kind of care.
Yeah.
And the reason why is I want to keep z, when I do take the partials of big G, when I get everything on one side and 0 on the other, I should put equals 0 here. I want the z partial, big G, z, if you will, to end up being a positive 1. So this right here is big Gy, and this right here is big Gx. Does that help?
Oh yeah, right. When you take the partial, then it would be 1 for GZ. Okay.
Yeah, and that'll ensure when the z component is a positive, that means I'm punching up. If you have a z component of a vector punching down, if it's a 3D vector, that means it's going to force the vector to be sort of somewhat in a downward position. Does that help?
It helps. Thank you.
Okay. So that's why you want to be oriented in the way that is tradition. Okay. And yes, it matters. And, you know, I don't have a lot of time since we're so jammed for time going over the end of the semester. So I'm not going to do a whole lot more examples, but we'll do some true falses right now. And then I want to talk about, if I can, greens, and because a lot of you got one of the problems on the quiz wrong. So I want to do that real quick if you'll allow me. So check out some true false, because there will be true false on the midterm this coming week, next week on Wednesday. Yeah, I always put a couple true false in there. You know me. Okay. So check out this true false. If the surface S is given by all ordered triples such that X lies between 0 and 1, Y also lies between 0 and 1, but Z is equal to X, then this scalar surface integral, okay, would be converted to a regular double integral where you'd have your dx dy and x and y are both going from 0 to 1. And then your density function fxyx, because it looks like they're replacing the z with x, which is good. And there you go. You have your scalar surface integral. True or false?
True.
Well, I'm going to give you a hint.
Okay.
Oh, right. No,
Understood?
yes.
So this is a big old false. Now, what should it be? Like if somebody said, well, it's false. Now what you going to do? Well, you'd have to get this big old yucky thing. And you've got your little z, which is also known as little g. So what is gx?
1,
Very good. And what is gy?
0.
Good. So this is square root of 2 dA. So what would fix this if somebody said, well, go fix it, so this is a true statement. You just got to put a big old square root of 2 multiple somewhere in the integrand, or I would actually just pull it out in front and then I'd be happy. Yeah. And then it's good. Then it would be a true statement. Do you see the difference?
Now I do.
This is key that you get this, because a common student error is, these flux integrals are the same double integrals I did last chapter. I'm good. I got this. Here, hold my beer. I got this. No, you don't, until you get the surface area element. Okay, here's another true false. I love these true false. Okay. Here, we're looking at a line integral. Oh, this is review from the beginning of this chapter. Let's see if you still remember anything about line integrals. Okay, fxy is continuous on a smooth curve. Fine. And then you've got your r of t is equal to x of t, y of t. That's a curve for time going from a to b. Then this line integral would be converted to a regular integral where you go a to b, and then you replace the x's and y's in your function with the x of t, y of t from the vector valued function. That looks good. And then your little ds, which is the arc length element, looks like they're replacing with a radical. Is this correct?
It had to be the speed.
Mm-hmm.
X squared.
So what's wrong here?
That 1 plus, they're
Yeah,
using
this one
surface.
plus, get rid of it. That's wrong. Yeah, that's not really speed. So this is a false because it should be the square root of x prime of t squared plus y prime of t squared, not with the 1 plus. That 1 plus is from the surface area element, not the arc length element. See the difference? I'm trying to pull a lot of these different ideas from this chapter together for you so you can be okay and see the differences. I don't know if that's helping or not. So what about the flux of a vector field across a curve can be computed using a line integral? We just did a flux across a surface in the last example, but can you do a flux of a vector field across a curve in 2D?
Sure. I think so.
You think so, or you know so?
I'm not totally sure, but I have a feeling, yes.
True, we just did it. It's the alternate version of Green's, which says if you're doing m dy minus n dx, that's equal to the double integral dm dx plus dn dy. And that gives you flux across a curve in 2D. Okay, so that's a true statement.
So essentially what we've been learning today was flux in 3D.
Yeah.
Okay.
But across a surface. And then Wednesday, we're going to learn flux some more, but across closed surfaces. So it's sort of going to be like the 3D version of this, of the alternate version of Green's.
Okay.
Okay. There's a media strip meme for you. Yeah.
I'll roll.
Love it.
Love it. Okay, now for those of you who are still with us, because I get that a couple people just bombed out. I get it. You're tired. But anybody knows your friends who like to leave my class early, please encourage them to watch the recording to make sure they pick up the last few minutes. Otherwise, it's not good. So I wanted to, I'm sorry, I'm looking for this solution to your quiz that I'm going to be grading this afternoon. Oh man, that's not it either. What the heck? I got too much stuff on here. Here we go. I got too many papers, and come the holidays, I got to clean up my office. Okay. So the problem that when I was looking at some of you taking this quiz, because yeah, I do watch you take the quiz, because that's what I do on a Sunday if I need to have fun. So here's a problem. I think it was problem 8 or 7 or something like that. So you had like y equals x squared was curve 1, and then it went up here to 1, 1, and then it went back here along the curve x equals y squared. Okay, and they wanted you, here's a force field, and yours might be slightly different because my math lab sometimes puts different numbers, but there's your force field. Okay, so they want you to get the counterclockwise circulation, and they want the outward flux. So these are 2 things that they were asking you to get. And in the problem, it said use both versions of Green's. And so that was what you were supposed to do. But a lot of people like choked on this, or at least the numbers. I haven't looked at your handwritten work yet, and definitely I give partial credit. So even though my math lab may have given you 0 points because your answer was, but so let's do outward flux first, okay? Outward flux, what Green says is, well, let me just tell you what the line integral would be. If you had to do the actual hard work with the line integral, it's mdy minus ndx. That's flux. And then you go, I'm not going to do the line integral because I don't have to. It's a closed curve and it's a nice simply connected region. Fantastic. And so then what you do is you set up a double integral instead, because who wants to do these silly line integrals with parameterizing and all that jazz? Takes too long. And then this right here is actually the divergence of f, which you guys have seen before, because that was another different problem on the quiz. Fine. So what is the divergence for this vector field? Well, oh crap, here's m, here's n, and I'm looking at dm dx, and I get 4y, and then plus the dn dy, I get -3. Oh, that's not too bad. Okay, and then I'm going to choose my order of integration to be dy dx, and if this is my region here, I could be really careful. X is going from 0 to 1 for sure. But y, if I put a little man in here, stand up, little man, his feet are on the lower limit of x squared. Uh-oh, am I allowed to put y squared right up here for his upper limit?
Oh.
No, that would be bad. So what you need to do is you need to solve x equals y squared for x, and for y rather, and you get plus or minus square root of x, but we're on the plus square root of x, so there we go. So I'll give you partial credit if you at least set it up like this. I'll be so happy you got it right. But I don't know why people bombed out here. But if you integrate this with respect to y, not too bad. I get 2y squared, minus 3y. And then you evaluate that between a lower limit of x squared, upper limit of square root of x. Ooh, okay. See, now this is maybe where it got messy. I don't know. So you're going to go 2, and then square root of x getting squared is x, minus 3 square root of x, and I'm just plugging in the upper limit, minus, and then when I plug in the lower limit of x squared, I get 2x squared x squared, which is 2x to the 4th, minus 3x squared. So this is what I still need to integrate with respect to x. So please be sure that you distribute this negative. That could have been a problem where some of you made a silly mistake. I don't know. It's kind of hard to say, but when you integrate this, I got what? X squared minus 3 times 2/3 x to the 3/2 minus 2/5 x to the 5th plus, because you got a minus there, x cubed, and evaluate between 0 and 1, and I got for the flux -2/5. Fine. Okay. So that's the flux. Now, what about the circulation? Oh, we got to get another meme here. Why did the chicken cross the media stream? Sorry, I have so many memes here. I don't even know what I have anymore. Okay, fine. So how do you get circulation of this problem? Well, it's the same region, And you're just going to go, you're computing the circulation as you're flowing around the outside border in that little paddle wheel. Or is the paddle wheel going to spin? And if it does, is it going to spin counterclockwise? That's if you would get a positive number. Or is it going to spin in the opposite direction? Or maybe it's not going to spin at all. Who the hell knows? So we don't know. So here's what we do know. To get this circulation, this is counterclockwise circulation. If you had to do the line integral, which thank God we don't, because we'd have to do 2 line integrals and add the results. We'd have to parameterize those 2 portions of the curve. I don't need to, because I'm going to convert this to a double integral. Fine. But then the integrand for circulation is dn dx minus dm dy. Oh boy. And then I'll choose dy dx if, for my area element, hopefully. So what is dn dx? Well, of course, that depends on your n that you got from my math lab. So for me, the derivative of 4x minus 3y with respect to x, that's not too bad. I got a 4. And then minus dm dy. So my m was 4xy plus y squared. So the derivative of 4xy plus 3y squared with respect to y is, oh, bummer. I get 4x plus 6y. So this may be another silly mistake that you accidentally made. You might have forgotten to distribute the minus, because if you did, then the whole thing went in the toilet, of course, because So after distributing the negative here, and then I'm going to set up basically the same, it's the same region. So x is still going from 0 to 1, and y is still going from x squared to the square root of x. And you know the drill. You're going to integrate with respect to y. Oh, man. Okay. 3y squared, and then evaluate that between x squared and square root of x. And oh, man. So, plugging in your upper limit first. Really? Oh, shoot. Yeah, this is kind of a nightmare. And then plug in your lower limit. Oh, boy. This is really going to be kind of yucky, but it's right now it's really just a calculus 1 issue. It's just algebra, and make sure you multiply your powers of x together. Here, this would be 4x to the 3 halves, and then you'd of course want to distribute your negative, and here you have a 4x cubed term, and you do all that. Okay, and so when I did all this integration, etc., I ended up with my counterclockwise circulation being negative 1/6, which means since it's negative, if I stuck that little paddle wheel in there, if the vector field was some water, shallow water, of course, because it would be 2D, whooshing around, my paddle wheel would spin in the clockwise direction and it wouldn't be going very fast because 1/6 doesn't have a very large magnitude. Okay, so counterclockwise circulation for me was negative 1/6, and my flux was negative 2/5. Okay, so I got 2 different numbers. Once in a while, you might get lucky and get the same number, but here we got, they're not related. You're computing 2 completely different things here. Flux and circulation are 2 completely different topics. Okay, questions on this problem that was on your quiz that you just took?
I'm good.
Okay. I'll stay for an extra 5 minutes. Other than that, I'm done.